Hey everyone, how's it going? My name is Sunny Beatteay, and today I'll be presenting from 15,000 database connections to under 100, a tech debt tale. Now before we begin, I just want to give a big thank you to everyone who's coming to see this live at the conference. I know there's a lot of great presentations happening right now, so I really appreciate you coming out to see mine. And a little bit more about myself. I am a software engineer at DigitalOcean. I've been at DigitalOcean for about 3.5 years, mainly on the storage team. I'm also a technical writer. I have a Medium blog, and I'm on Twitter. But while I am a software engineer, I'm not coming to you today as a software engineer. No. Today, I'm coming to you as a historian, because I'll be retelling the largest tech debt overhaul, the story of the largest tech debt overhaul at DigitalOcean to date. It was a multi-year effort that spanned between roughly 2016 to 2018 or late 2018. And it was a cross-team collaboration. Basically, the entire engineering organization was involved in this overhaul, say. But before we get to the heart of the story, the 2016 era, I want to first show you a little bit how DigitalOcean is nowadays and how it was the founding and kind of work our way there. So, DigitalOcean nowadays. If you aren't familiar with DigitalOcean, we're a cloud provider, much like AWS, GCP, or Azure, but to a much smaller scale. We offer infrastructure as a service offerings, so we have things like virtual machines, virtual private servers, load balancers, that kind of stuff. And today, we look pretty nice. We have a nice logo, you can see in the top left. We have a nice mascot as well, same with the shark. You can see the stickers in the bottom left. And we have our web application. And you can see, as I mentioned, we have a number of products in our catalog, virtual private servers, Kubernetes, volumes, all kind of good stuff. But it hasn't always been this way. So let's go back in time to the year 2012, when things weren't always this nice and were a little more simple. So you can see back in 2012, when DigitalOcean launched, things looked a little more simple. Logo was a little more simple, the mascot a little more simple, and our product catalog was also a little more simple. Back in 2012, we only offered the virtual private server offering, which we called droplets. So you might hear me say droplet quite a bit. So if I ever say droplet, that's essentially a virtual private server. And while things were a little more rudimentary back then, they still were simple, because simplicity has been one of DigitalOcean's key values since the very beginning of its founding. Both the product offering, but also, more importantly, in its technical architecture. So DigitalOcean, much like GitHub, Twitter, and Shopify, started out as a Ruby on Rails monolith. So you can see on the left side, Rails powered the user interface, so both the web application as well as the API, so everything customer facing. We also had some backend services, so some that were written in Perl. One of them was called Scheduler. Scheduler was in charge of actually scheduling the VPSs or the droplets onto the hypervisors. And then we had another backend service called DigitalOcean Backend, or Dobie for short. And Dobie was in charge of actually creating the servers on the hypervisors, or the virtual machines on the hypervisors. And one important thing to note about Dobie is, since it was actually in charge of creating the droplets, or the VPSs, it's ran on every hypervisor in our server fleet. Meaning that if we had 100 hypervisors, we also had 100 instances of Dobie running. Now, the way that these backend Perl services talked with the Rails frontend was through a MySQL database. More specifically, a table in the MySQL database called the events table. And this table acted as a sort of message queue. And if I was a customer back in 2012 that wanted to create a droplet, I would go to the UI, click a button, and the UI would say, droplet being created. Behind the hood, or under the hood, what would be happening is the Rails application would insert an event record into the events database. This event record would have a couple different properties. It would have a type, so what kind of type of event it would be. In this case, it would be a creative type. It also have a server ID and a status. So initially, the server ID would be null, and the status would be pending. And then what would happen is Scheduler, on a infinite loop, will be polling the database for new unscheduled events. And the way that it knew it was unscheduled is because the server ID field would be null. So scheduler would pick up all these unscheduled events, assign them to a hypervisor, and update the record with the ID for the hypervisor, in this case, the server ID. So for example, it might assign it to the server ID of 3. Next, what would happen is Dobie, also much like scheduler on an infinite loop, polling the database every couple of seconds for all these scheduled create events, would find these scheduled events. Now remember I said that Dobie ran on each hypervisor in the fleet. So in this case, the Dobie that ran on server ID 3 would pick up this new event and see there was a create event. So it would create the droplet on the hypervisor and then update the record to done. So this is how the system knew that this event had finished. Now I know this is an SRE conference, so I'm sure there are many SRE engineers and architects looking at this architecture and a little groaning to themselves a little bit, because admittedly there are quite a few shortcomings with this system. But one thing that's important to remember is that back in 2012, the staff the engineering staff that was in charge of this architecture was quite small. There was only 3 engineers in charge of architecture. And what was also small was the user traffic for this application. So you can see for the first year of DigitalOcean's launch, traffic was pretty minimal. You had, for the first 6 months, less than 100 droplets per day were being created. Not very much. After 6 months, you see a little bit more traffic, but it wasn't until the beginning of 2013 when you see 2 big spikes. Now you might be wondering what caused those spikes. Well, funny enough, those spikes were actually caused by Hacker News. Yes, Hacker News plays an important role in DigitalOcean's history. So each spike can be contributed to a different article or a Hacker News article. So the first one was a TechCrunch article talking about how DigitalOcean switched to using solid-state drives for their VPS offerings. And the second one was a blog post comparing the benchmarks for Linode and DigitalOcean. So once both of these articles went live on Hacker News, it put DigitalOcean on the map. And it began what I call the market fit phase. So you can see for the first 6 months of 2013, after those articles came out, traffic exploded. And it went from roughly, a couple hundred droplets per day to now upwards of 2,000 per day on a good day. It got to the point where we got some notable news in it. People started noticing DigitalOcean a little more. You can see for the first 6 months from December 2012 to June 2013, we got a 5,000% increase in growth. Now, when you're starting with small numbers, like 138 servers, it's pretty easy to get 5,000% growth, but it was still pretty notable. But the one important thing to say about this traffic is that once the company started growing, we went from, instead of focusing on designing the product, we went from focusing on growth, hiring new engineers, and essentially now adding more and more features to the product. So what that meant is that this architecture was here to stay. There was too much traffic to now go back in time and try and re-architect it. We had to scale with what we had. So essentially we took on tech debt to scale architecture and meet the demand of the customers. And as I said before, there are some notable shortcomings with this architecture. There's a number of bottlenecks and single points of failure. So if any component in the system failed, basically the entire system failed. It was also quite unoptimized, more specifically for concurrency. So it wasn't concurrent whatsoever, essentially. So what that meant is that it's very vulnerable to high periods of traffic and bursty traffic, which definitely happened during those times. But despite all these flaws, we were still actually able to scale the system for quite a while, for 4 years, in fact, actually. So if we skip ahead 4 years, we'll get to 2016, the beginning of the story. So in the time between 2012 and 2016, we did make some improvements to the architecture. We went from, before we were using Perl for a lot of the backend services. Well, we switched to using Go for primarily our backend services. We also switched from HTTPS to gRPC protobufs for mainly internal architecture or internal communication between the services. And we also split out a lot of these services from a monolith into microservices. Now, I know there's a lot of debate still about whether microservices are an actual improvement over monoliths, but for the sake of this story, we're going to say it was an improvement. But despite these kind of small improvements since in the 4-year period, the high-level architecture looked pretty much the same. The only difference you can really note is on the left side. Instead of Rails being the component that pushed the events directly into the database, now we have a microservice called the droplet service that did that. But other than that, that was pretty much no change had really happened to the system. But what did change, however, was the amount of traffic. So you can see there was quite a bit of growth between 2012 and 2016. I mentioned before, around 2013, we're getting around 2,000 droplets being created per day. Well, now in the beginning of 2016, we're seeing around 30,000 being created per day. So a much larger spike in traffic. That was about a 1,500% growth in that 4-year period. And what that meant was there's a lot more pressure on the system. So the more users creating droplets and creating products, the more requests that our service got, the more create events that were being pushed into the MySQL database. The more events in the MySQL database meant scheduler had more and more events to schedule, essentially. So it had to pick up more and more of those droplets in order to schedule them onto the hypervisors. So scheduler was also working overtime. And with more users creating more resources, DigitalOcean had to buy more and more hypervisors to keep up with the demand. So the more that people bought, virtual machines, we needed to have the capacity to keep up with that. And as I mentioned before, each hypervisor ran an instance of Adobe. So the more hypervisors we bought, the more instances of Adobe that were directly connected to the database, polling for new events. So Adobe was also working overtime. And you can kind of see where all the arrows are kind of pointing to. And it got to the point where we were buying so many servers and running more and more instances of Adobe that at the peak of this architecture, we had 15,000 database connections, all connected to that central MySQL database cluster, polling for new events every couple seconds. One other thing to note is that in that 4-year period between 2012 and 2016, we had added more products to our catalog. So it wasn't just VPSs anymore. We had firewalls, we had load balancers, those kind of things. And with every product that was added, the SQL query that Adobe used to poll the database for new events got more and more complex over time, to the point where it was essentially dubbed the God query. So I've blurred out all the information to, blurred out all the sensitive information. But you can kind of see the structure of this query, and it's pretty massive. It spanned over 150 lines and joined across 18 tables. It was as impressive as it was precarious. So now imagine 15,000 database connections all running this query on a single database cluster. The database cluster is not going to be very happy with that. And it got to the point where we had outages, or it kind of came to a head during a couple of key outages where essentially the database went down, and the backlog was so long that normally it takes just like over a minute to provision a droplet. In this case, it was taking upwards of an hour. So those kind of instances made us realize that we had hit our scaling limit. Because no matter how bad or good a system is, every system has a scaling limit, and we had hit ours. So the engineering team knew that we had to basically improve it. We had to go back to the drawing board and come up with improvements to the system. But there's some key issues. Most notably, as I mentioned before, there wasn't just one bottleneck in the system. There are multiple bottlenecks in the system. So it wasn't enough to just pick one part of it and improve it and call it good, because that would just kind of kick the can down the road and move the problem to a different part of the system. We had to come up with essentially a holistic approach and come up with a plan to improve every component of the system one by one. And that's exactly what the team did. They came together and decided on a plan of action. And the first thing they decided to work on was the biggest elephant in the room, which was the number of database connections. So the first task on the list was to just decrease the number of database connections, or direct database connections. And so in order to do that, they had to focus on the Adobe part of the system. Now, at this point in time, DigitalOcean was running in multiple data centers, and each data center had hundreds of servers, and each server was connected directly to that MySQL database, pulling for new events. Well, the team thought, well, instead of having every server in every data center pulling for new events, why not just have one service in every data center dedicated to pulling for new events, and then it would just push those events to the appropriate hypervisors. So instead of having each hypervisor pull for its own events, have a routing system for that. And so they came up with Event Router. And so Event Router was designed to be a regional and data center proxy that pulled for new MySQL or for new create events on the MySQL database, and then push those events to the appropriate Adobe instance. So it's kind of a pull and push model a little bit. So it basically just routed the traffic. From a high level view, it looked a little bit like this, where we had the MySQL cluster in the center, and then each data center had a highly available deployment of Event Router pulling for new events for that data center, and then each of the events will be routed to the appropriate hypervisor with a server ID. And so in the kind of longer diagram, this is how it looked when Event Router was added in. So instead of hypervisors pulling for new events, we had Event Router there. And this was a major feat. It took a while to actually do this, much easier said than done, but we were able to actually create this. And Event Router in itself was actually enough to decrease the number of direct connections from 15,000 to 100. So we had done it. The title of this talk is 50,000 to less than 100. We had done it. But as I mentioned, there were multiple problems to the system. It wasn't enough to just tackle the direct database connections. There was other things on the list that we had to focus on. So while this was a huge feat and we were happy about this, there was still some more work to do. The second major issue that we tackled was improving the scheduler's availability and performance. So in order to do that, we had to address the scheduler part of the system. So I haven't talked too much about scheduler at this point, but to give a little more information about it, as I mentioned, scheduler was written in Perl. It was single-threaded, so it didn't have any concurrency whatsoever. It was also not highly available. It was not a highly available system. There was only one instance in charge of scheduling for new events for the entire server fleet. So really precarious. If it went down, that was it. It also had multiple dependencies on the MySQL database. As I mentioned, it pulled for new events, for new unscheduled events, but in order to determine which hypervisor each droplet should be assigned to, it also fetched the server metrics or the hypervisor metrics from that same central database, because we stored all the hypervisor metrics in that MySQL database. So Scheduler v1 had multiple dependencies on the database, which was not good. We wanted to remove as many dependencies on the central database as possible. And lastly, the logic that Scheduler actually used to rank and kind of sort and determine what was the most available hypervisor to be assigned to was quite complex. Here's a little snippet of it. This was the scheduler's ranking logic to determine which hypervisor should be assigned to. Basically a big if-else statement. This is our scheduling machine learning model, essentially. So in order to prove all this, we came up with Scheduler v2. So Scheduler v2 was meant to basically address all the issues of Scheduler v1. It was highly concurrent. It was written in Go, so we had a good concurrency model. It was also highly available for deployment, so it had multiple replicas, so that if one went down, another one could pick it up. But most importantly, instead of fetching the hypervisor metrics from the database, it would scrape those metrics from the hypervisors themselves. So we expose the metrics on the hypervisors for things like CPU usage, capacity, disk space, all that stuff. Scheduler v2 would scrape all those metrics, store it in its own data store, and then use that data store to do the improved ranking algorithm. So that essentially removed one crucial dependency from the database. So when Scheduler v2 went live, this is kind of how it looks like. We have Scheduler v2 to replace Scheduler v1, and we have Scheduler v2 also scraping those metrics from the hypervisors. And when Scheduler v2 went live, it was essentially, it took the better part of 2016 to create both Event Router and Scheduler v2. So at this point, when Scheduler v2 went live, it was now 2017. And it was a really important thing that we had created both Schedule V2 and Event Writer, because it meant our system could scale even more now, which is great because in that year, we had scaled quite a bit. So in 2016, we were seeing roughly 30,000 droplets being created per day. At the beginning of 2017, we were seeing upwards of 100 to 140,000 being created per day. So a big increase in that time. But what that also meant was that the part of the system that we had not addressed yet was seeing a lot of load. And that was mainly the message queue event table and the droplet service. So at this point in time, the events table was seeing 400 new records per day and 20 updates per second on those records. And remember, this was just one table in the database. This was like a database in heavy use for other things too. So we had just one table that was seeing this level of traffic. And another issue with this is that, as I mentioned, in the time between 2012 to now, we had added more and more products to our catalog, and each product had its own service dedicated to it. So it wasn't just Droplet that was creating new events into the MySQL database. We also had load balancer, firewalls, other things, all pushing new events to the events table. And so the problem with that is you don't want to have a lot of services all with a direct connection to a single database, because it can be really hard to audit all those connections. And when an issue comes up, it can be hard to determine which service is causing those issues. And also, when you have multiple services all fighting over a shared resource, especially if that resource is a database, you're going to get table locks and query backlogs, especially during periods of really, really high traffic. So that brings us to the third and last major improvement that the team wanted to make, which was we wanted to absolve the database of its message queue responsibilities entirely. And this was by far the biggest undertaking, because the database was a crucial part of the system. So to try and remove that from the system was going to take a lot of work. And so in order to do that, the team came up with a service that we called Poon. So Poon was meant to be an event aggregator and a database proxy, essentially. So it was basically an API layer in front of that database. And it was meant to be the sole access or the sole publisher to the events table. So instead of having all the services with a direct connection, now we would have all the services pushing directly to Poon, and then Poon would then push those events into the database. So that was the first step, which is to basically create an API layer. And the easy part was actually creating Poon. The harder part was getting buy-in from the rest of the company to actually use Poon. Just because you build it doesn't mean teams will want to use it. And remember, at this point, teams that had been so used to having direct database access for so long that it was kind of a big ask to not only take the time to change your code in order to integrate with this new API that had been built. It was a lot to also give up that direct database access, because there's a lot of flexibility with having access to a database. So even though the teams all kind of knew this was the best route to go, when it takes effort to change your code and integrate with a new service, it could take a while to do that. So our Poon team knew this. So they went team by team, service by service, and talked with them, trying to get buy-in to have the team integrate this new API and work with them to change the code in order to utilize the API. And this in itself took a long time. It took basically the better part of 2017 just to get buy-in from the rest of the teams to use the API. But it did happen eventually. So by the end of 2017, Poon became the sole publisher of events to the MySQL database, which was a huge feat. But it was also just step one. That was just the first step in this process, because now that Poon had an API in front of the database layer, it was now free to basically re-architect and re-implement the entire event model. So we had, before it was all based around the database. So we had to basically come up with a replacement for the database using something that was a little better suited for the message queue, like a high throughput message queue. So what Poon ended up doing was using a essentially turning to RevMQ. So using a queuing service with workers that pull the events off of that queue, which is a huge shift because we essentially went from a pull-based model with schedule v2 and event router pulling for new events and polling the database to now a push-based model where Harpoon pushed new events to the queue, and we had workers who would pull the tasks off and then direct those tasks to each service. So whenever a user now creates a droplet, Harpoon pushes the event or the task into the queue, a worker pulls it off, and then now communicates with scheduler v2 to get the appropriate hypervisor. And then once it gets the hypervisor, it can now direct it to the data center with the hypervisor in it, and event router can take care of the rest. So that was essentially the big overhaul that Harpoon team did. And as with most things, it took a while to do, but we finally got it done in around mid-2018. So with all of those things in place, this is now how the event architecture looks like. So you can see DigitalOcean has grown quite a bit from its garage brand roots in 2012 to kind of now where it is today. So to wrap up this presentation, I just want to go over some of the key lessons we learned during this entire process. So the first one was to start simple. I know I poo-pooed a lot the initial architecture that the founders came up with, but they got one crucial thing right, which was to start simple and to keep the system easily understandable and easily maintainable. You know, despite the fact that it had some anti-patterns and that, you know, it was a little finicky, we at least knew about those issues and we were able to kind of work around them. And it was also, because it was so simple, it was very easy to onboard new engineers into the system and then get them up to speed. That was one of the key reasons why we were able to scale for as long as we did. But inevitably, you can't scale forever. Which brings me to point number 2. Is that every system has a breaking point. And it's really important to learn when your breaking point is coming. You know, it's not always possible. That's something that we're still learning to this day. But there are usually key indicators. You know, are instances increasing at a faster rate? Are things just breaking more often? You know, those are really key signs that the system has trouble. That was something that we definitely saw coming. And, you know, there's time for patches and for hot fixes that can kind of give you a little more longevity. But there's also time for refactoring and just kind of re-overhauling the system so that you have a longer runway for that system. Another key lesson we learned was that software is hard, people are harder. And we definitely learned that quite a bit during the Harpoon phase of our story. Because just because you built something doesn't mean people want to use it. And especially when you're building something that affects everybody, you want to make it as easy as possible for people to integrate with it. Ideally, you want to make it so they have to do anything, and then it'll be really easy to get by in that case. But if people do have to make effort to actually integrate with your services, then it's important to work with them. You know, work with them to get by and help them integrate with that service. That was a key thing that the Harpoon team did in order to get people on board, because people management is as important, if not more important, than software management. And the last big lesson we learned was to learn as you go, because it would be great if we could foresee all the issues that are going to happen, but that's not the case. We can't predict everything. Unforeseen issues, edge cases, all things are always going to come up. And as software engineers, we have to roll with the punches, and also SRE engineers as well. You just have to roll with the punches. You know, tech debt is a normal part of working in the tech industry, but tech debt isn't the biggest. You know, tech debt itself is not the big issue. It's how you deal with the tech debt when you have to. And whether it's breaking apart single points of failure, decoupling components, or crafting multi-regional services, we as software and SRE engineers are always looking to craft elegant and simple solutions. Thank you very much for listening to this talk. I hope you found it very beneficial. I have my contact information on the slide as well if you want to contact me after the talk. And I am more than welcome to take questions right now. Thank you very much.